So in this lecture I will be talking again about logistic map. Parameter are between 0 and 4 and U node is in the domain 0, 1. So what we found, so this solution is U2, we remember this, it is stable up to this point and here it becomes unstable. These solutions are U3 and U4, which form, they're not fixed points in terms of logistic map, but they form two periodic solutions. So it's flipping between U3 and U4. And this two periodic solution occurs when R equals to 3 and becomes unstable when R equals to 1 plus the square root of 6, I remember 3.40 something. And then we know that we will have period doubling cascade and around the value of 3.54 somewhere here. So we have solution of periodicity 2 to the power of n, or 2 to the power of infinity. So that we have here chaos. But what happens? So our R changes up to 4. So we have a range from around 3.54 up to 4.0. So what happens in this range? In this range, we can eventually have solutions of other periodicities. So at this point, at 3.54, we have periodic solutions like of periodicity 2 to the power of n for any n, but all of them unstable, all of which unstable. And therefore we have chaos. It's why we have chaos. But if we will look here, we will see that, for example, here at 3.80 something, we have stable 3 periodic solution. Somewhere here, we have stable 5 periodic solution. Somewhere here, if we check it, it will be stable 6 periodic. So eventually we will have solutions of all possible periodicities, but they appear in some strange order. And this order is given by so-called Sharkovsky order. So we have, it looks like this. We have fixed points, then we have 2 periodic solutions, and we have 4 periodic. When we have 4 periodic, we also have fixed points which are unstable, and 2 periodic, which is also unstable. Then it will be 8 periodic, then and so on. It will be 2 to the power of n for all possible n's, 2 to the power of n plus 1, and so on, up to 2 to the power of infinity. And then there will be up to 2 to the power of infinity, and then eventually will appear solutions which are not powers of 2. It will be 2 to the power of n times some odd number, 2k plus 1. And then there will be, then this n now gets down for 2k plus 1, and then we will have 2 to the power of n times, let's say, 9, then 2 to the power of n times 7, 2 to the power of n times 3, and then it will be 2 to the power of n minus 1, say, times again 9, and so on. And at the end, so here r is increasing. So this, in this direction, r is increasing, and finally there will be just odd periodicities like 2k plus 1, so on. Then it will be 9, 7, and 3, 5, and 3. And the point here is, when we know that we have 3 periodic solutions there, up to this point, not all periodicities are covered. But then, when we have 3 periodic solutions, we have solutions of all possible periodicities, but eventually they all are unstable. So the order is put it like this. So 1 less than 2, 2 less than 4, 4 less than 8. So this less means they appear for lesser value of r. Less, and so on. So this is called Sharpinsky order. So I will refer to this point. So at this value of r 3.87 or something like this, I don't remember this exact value, when we have 3 periodic solutions which are stable, so at this point we have solutions of all possible periodicities, but all of them unstable except for 3 periodic. But then 3 periodic also becomes, when it becomes unstable, we have all possible periodicities which are unstable. And then eventually there can, some of them, like we can have more than one, for example, 6 periodic solutions. And eventually, after 3 periodic solution becomes unstable, there will appear 6 periodic solution which is stable. But 6 periodic solution also was appearing already earlier. So this is a bit messy how it appears, but at least this order is given by Sharkovsky, by this kind of inequalities. Up to now, I was presenting all results only for logistic map, but in fact, these results are also valid for many other maps. And I want to show that all so-called quadratic maps are isomorphic, or what is observed in one of them is also observed in any other. So let's talk about quadratic maps now. So quadratic maps, we can put it like this: un plus 1 is, well, just similar to linear maps. We need some parameters: a un squared plus bun plus c. So for all possible values of a, b, c are parameters. For example, if we say a equals to minus r, b equals to r, and c equals to 0, we will have un plus 1 equals to run 1 minus un. So this is logistic map. But in fact, a, b, and c can be anything. So this statement is quadratic maps isomorphic. they can be converted to each other. So this I will illustrate it by converting to logistic map. Let us convert logistic map. So this conversion can be done by changing variables, by transformation of variables. Logistic map, say we have un plus 1 equals to r un 1 minus un into another map, So I will put it like this. Yn plus 1 equals to 1 minus a capital, its parameter 0, times yn squared. So this logistic map, and this is another quadratic map. So we consider transformation of variable u to variable y. It's linear transformation. We consider linear transformation. And so what we want to find, we want to find alpha and beta such that logistic map is converted into this another map yn plus 1 equals to 1 minus a yn squared. So we have logistic map, and we will use this transformation. Yn is alpha y, un is alpha yn plus beta, and un plus 1 is alpha yn plus 1 plus beta. So this we put here, and this we put here. So after putting this, what we get is alpha yn plus 1 plus beta is equal to r times alpha yn plus beta times 1 minus alpha yn minus beta. After opening brackets and we take beta on the other side, alpha yn plus 1 will be equal to minus beta, and we open brackets. So this is so after opening brackets we will have minus r alpha squared yn squared plus r alpha 1 to beta yn and plus beta r minus r beta minus 1. Finally, after division by alpha, we will get yn plus 1 equals to minus r alpha yn squared plus r 1 minus 2 beta yn and plus beta or alpha r minus r beta minus 1. And we know that yn plus 1 should be equal, so this yn plus 1 should be equal to 1 minus 8 times yn squared. And from here we conclude now that minus R alpha should be equal to minus A, three terms. So linear term should disappear. 1 minus 2 beta equals to 0. And last term, free term should be equal to 1. Beta over alpha times R minus R beta minus 1 should be equal to 1. Now from first equation we get alpha equal to A over R. From second we get beta equals to half. And from the last we get R over 2A times R minus R over 2 minus 1 equals to 1. So we here beta is half and alpha is this. So we take this alpha and put it here. And from here, finally, we have expression for A. We can find expression for A equals to R over 2 times R over 2 minus 1. So what conclusions now we can make from what we found here? We know, for example, in the logistic map, when we have bifurcation, when R equals to 1, and from here we can expect that for yn plus 1 for this map 1 minus a times yn squared, we will have bifurcation at value of a, which is so r over 2 minus 1, and this will be half minus 1, it's minus quarter. So this here we will have bifurcation. And similarly r equal to 3 when our first period doubling appears. For this we can find a 3 over 2 minus 1, and this will be equal to 3 over 4. Here we will have two periodic solutions. In our second map. So this way, if we find correspondence between quadratic map and, for example, our logistic map, we can transfer all our results about logistic map to another quadratic map.